To monitor a space effectively, an autonomous surveillance robot must constantly evaluate human behavior. It has to distinguish between a person walking through a room and a person loitering suspiciously. The raw object detection model running on the system, YOLO V8N, cannot make that distinction. It processes video one isolated frame at a time, with no memory of what happened a second ago. To bridge this gap, we implement a custom ROS2 vision perception node. This node subscribes to a live overhead camera feed running in a gazebo simulation, tracking the movements of human actors within the environment. Its primary function is to ingest a continuous 30 frame per second video stream and output discrete navigation commands. By engineering a layer of short-term memory on top of a strictly stateless model, the robot gains the context required to make complex decisions entirely on its own. When we execute the launch command ROS2 run vision perception YOLO node in the terminal, the system initializes. An OpenCV debug window immediately opens, providing a real-time visualization of the node's internal processing loop. In this frame, you can see how the node evaluates a stationary actor. The system calculates a minimal pixel velocity of 11.1 pixels per second and applies the label staying. When an actor begins moving at a moderate pace, the node detects the change. The velocity calculation climbs to 75.7 pixels per second, and the label updates to walking. For fast-moving targets, the output shifts again. Here, an actor moving at 242 pixels per second is instantly reclassified as running. The node constantly monitors these states to evaluate threat levels. If an actor's classification remains on staying for 5 seconds, the system triggers a suspicious event. This debugging window provides direct proof that the node is successfully extracting abstract pixel data and mapping it directly to concrete human behaviors. This logic flowchart outlines exactly how the vision node processes a raw camera frame and routes it through the YOLO detection logic. Every step in this sequence executes inside a single ROS2 function called image callback. The overhead gazebo camera streams video hardware output at a constant 30 frames per second. However, the perception node intentionally intercepts only about 6 frames per second, activating roughly every 0.15 seconds. Running YOLO inference algorithms on all 30 frames would instantly saturate the robot's CPU compute capacity. Dropping 24 frames every second is a deliberate architectural constraint built into the node. In a live robotics environment, aggressive rate limiting preserves the computational bandwidth required to run the heavy navigation and path planning algorithms operating in parallel. To compute velocity, the system must extract movement data from isolated bounding boxes. The node stores the exact center coordinates of the bounding box in its internal memory. The node plots the new bounding box center alongside the previous frame's coordinates on a grid. Connecting these points forms a right triangle, representing the change in x and y. The Euclidean distance formula yields the spatial distance the box moved. Dividing that spatial distance by the exact elapsed time yields the final pixel velocity. This precise velocity calculation executes constantly in the background for every single isolated frame the vision node decides to process. Standard geometry turns a sequence of stateless images into a dynamic velocity vector. Raw pixel velocity provides no actionable context for navigation. It must be categorized. This table outlines strict boundaries. Velocities under 20 pixels per second are labeled staying. This buffer accounts for bounding box jitter, ignoring microscopic shifts. Velocities between 20 and 150 are walking, while anything over 150 is running. The moment a velocity value falls into one of these brackets, the corresponding yellow text updates on the OpenCV debug interface. By enforcing these rigid thresholds, the node filters out hardware noise and stabilizes the robot's overall perception of the environment. This final section of the logic flowchart controls the system's temporal loitering check, dictating when to publish a goal. An actor pausing for a split second does not constitute a threat. The system demands temporal confirmation before acting. When the system classifies an actor as staying, as seen in this frame, a localized timer immediately activates and begins counting up. This timer is highly fragile. It requires absolute continuous stillness to progress. If the actor's velocity spikes above 20 pixels per second, the internal variable tracking the start time is immediately nulled. Once that timer breaks, the 5-second countdown must restart entirely from 0 the next time the actor stops moving. The logic loop only succeeds if the timer hits 5 continuous seconds of staying without a single interruption. This temporal state machine serves as a strict safeguard, ensuring the robot only mobilizes for genuine loitering behavior. Once the 5-second condition is satisfied, the perception node triggers its final operational function: send goal to person. This diagram shows how the alert is packaged into a ROS2 pose-stamped message. The node attaches a timestamp, assigns it to the map frame, and embeds the target coordinates. A 15-second cooldown timer activates, preventing the node from spamming the network with duplicate goals. The packaged pose-stamped message is then broadcasted across the ROS2 network via the /goal-pose topic. Inside the terminal, the node logs a clear confirmation, goal sent, followed by the specific coordinate values. The YOLO node completes its pipeline, handing off all physical execution to the custom navigation stack. Through a precise sequence of pixel mathematics, rate limiting, and time tracking, a raw camera feed successfully commands an autonomous robotic response.